Hi, so in today's class, we'll want to talk about entropy changes, right? I want to go back and look at entropy a little bit, and more specifically, I want to talk about how to calculate standard entropy changes for a reaction. So, if we remember back to enthalpy back in chapter 7, we first established calculating, or we worked with standard enthalpy changes of reaction, right? We calculated them. And so just a few reminders of what we mean by standard. So just first of all, the little degree sign here, right? That is our indicator that we're working under standard conditions. And if you don't remember, this RXN, right, is the little abbreviation we use for reaction, right? So we see this is the value for a reaction. And we've defined earlier in chapter 7 what standard state means for a material, but just to go back over those. For a gas, a standard state is the pure gas at 1 atmosphere of pressure. So the pure gas with a pressure of 1 atmosphere, or we could think of it as a partial pressure of 1 atmosphere. For a liquid or solid, the pure substance in its most stable form at 1 atmosphere and the temperature of interest. So in other words, we're at 1 atmosphere pressure, and whether it's more stable as a liquid or a solid at that particular temperature, that would be its standard state. Now, usually the temperature we define it at 25 degrees, but it could be at any temperature, right? If we, define it at 25 degrees, well, then the standard state, for say water would be a liquid, right? And if we have an aqueous solution, the standard state is a 1 molar concentration of that solution. So that's a little review of what we mean by standard state. So now we can turn toward actually looking at how we get to those standard enthalpy changes. So one of the first things we need to look at when we start trying to think about standard entropies, right, is how we define them relative to a 0 point, right? So if you remember back to enthalpy in chapter 7, right, there is no absolute zero for enthalpy, right? So we had to define a relative value. We had to come up with, if you recall, these delta H's of formation, right? And we could define the formation of an element from itself, right, as 0, right? So we used these enthalpies of formation to define a relative 0 point, right? Because there was no absolute 0. Now, however, for entropy, right, we have an absolute 0, right? And this is told to us, or we can think about this by looking at what we call the third law of thermodynamics, right? So the third law states that the entropy of a perfect crystal at 0 Kelvin, right, absolute 0, is 0. So in other words, right, there is no disorder, 0 entropy for a perfect crystal at absolute 0. Right? Okay. So that's our absolute 0, right? We don't need to come up with other values like standard enthalpies of formation because we have one. Now, if you want to think about why that is the case, how can we sort of prove that is the case? So if we remember, Boltzmann, right, defined entropy as S equals K times the ln of W. So in a perfect crystal, W would be 1, right? And so the natural log of 1 is 0. So the entropy would be 0 at a perfect crystal at 0 Kelvin, right? There's only one state because there isn't any vibration, right? There's only one possible state. And so the idea is that entropy would be 0. And that's our third law. And so the absolute entropy of a substance is the amount of energy it has due to the dispersion of energy. So everything that is not a perfect crystal at 0 Kelvin will have some amount of entropy. And so everything is relative to this 0 point. So with that being said, one thing to keep in mind is that all standard enthalpies, or all of these entropy values, will be positive numbers, right? No negative entropies here. So just to go over a few sort of formal ideas, right? We abbreviate the standard molar entropy, right, as S with the little degree sign. It is an extensive property. So remember, this means that it changes with amount. So if you have more material, the standard entropy will go up. So we typically define in tables the standard molar entropy, right? So the value for 1 mole. And so we say that 1 mole of a substance, typically at 25 degrees or 298 K, for a particular state, right? Whether it's solid, liquid, or gas, a particular form, or what we call allotrope of that material, a particular, molecular complexity, right, for a molecule, with a particular molar mass, and whether it is dissolved in solution, right? So these are things that can affect the value of the entropy, right? So in the table, we'll specify certain things. We'll specify the state that it's in. Is it in solution? Is it a particular allotrope, right? And of course, complexity and molar mass are determined by the chemical structure. But those things can influence the entropy. And in a little bit here, we'll talk about how these things will influence the entropy. So if we just look at a table, there's not a whole lot, specifically I want to point out, except for there will be a much bigger table in the appendix, right? The same appendix that we've been looking at, right? It's the first table in Appendix 2, and it lists all of our thermodynamic values, right? We use the values of delta H before the formation values, right? So in that same table, you're going to find standard molar entropy values. You will also find delta G values, or free energy values, in that same table for the same materials. So you're going to look up all these values in the appendix when you actually go to solve problems for them. But notice that we have only positive values. We make sure and specify the state of matter, right? Because it's not going to be the same for gaseous water and liquid water, right? Clearly the entropy of this gas is going to be bigger than the entropy of the liquid, right? And so forth, right? So we're going to specify the state. We're going to specify, what the material is in the table. So now I want to look at some of these factors that can influence the standard entropy of a material. So the most obvious one, right, is its state of matter, right? So a solid, a liquid, or a gas. So we looked at earlier, right, we determined that the gas is going to be the highest entropy state, the solid is going to be the lowest entropy state, and a liquid will be somewhere in between, right? Based on how much freedom of motion those various states have. And so we can clearly see that from this simple example with water, right? Where we see that the entropy of the gas is much larger than the entropy of the liquid. Right? So the liquid state has a larger entropy than the solid. Now I didn't list the solid here. And the gas, of course, will have a larger entropy than either the liquid or the solid at a given temperature. So state of matter is one factor. Now, the relative molar mass, right, will also play a role here. So the larger the mass, the larger the entropy. So heavier atoms will have higher entropy than lighter atoms. Now, this has to do with, in a structure, the heavier atoms will tend to be closer to each other, allowing more energy dispersal through the different energy states. Now, the details of this are beyond what we need to talk about now, but what we want to understand at this point is that as mass goes up, so does the entropy. Now, another thing that can influence that is if the material exists in different common allotropes, then those allotropes will have different entropies. So, for example, the two allotropes of carbon, or two of the allotropes of carbon, are diamond and graphite, and we can see that diamond has a lower entropy, meaning it's a more ordered system than graphite, right? And so, if we look a little bit at the structures, right, diamond is very ordered, right? It is, each carbon atom is covalently bonded to 4 other carbon atoms. We get a series of tetrahedrons, right? Very ordered. Whereas graphite has 6-membered rings of carbon, right? So that part, but it's in sheets. Notice there's no connecting of the sheets. They're connected just by intermolecular forces, and so these sheets slide past one another, right? Which is how, pencil works, right? The graphite slides off the edge. So that allows for more disorder, a higher entropy value. So the form of the material, or the allotrope, can play a role. Molecular complexity, how complex, right? Are there bonds, right? Are there more than one atom involved, right? Etc. So, larger, more complex molecules will generally tend to have larger entropy values. So, if we look at our first example, where we have an element argon versus a diatomic NO, right? While these materials have about the same molar mass, so notice we've tried to keep molar mass similar so that we can do a little bit of a comparison. You can see that the more complex NO has a higher entropy value, right? With that and having that bond brings on more potential for disorder, right? If we look at a second example where we go from something that just has 2 atoms bonded to one another, where we have 6 atoms with multiple bonds, like different things bonded to each other, right? Again, similar mass. We see that the more complex material, right, has more entropy. So the basic idea is that the more complex the molecule, the more entropy it has. Now this can get a little more complicated if you're comparing things that have widely different molar masses. So maybe you have a simpler complex, but it has a larger molar mass because the atoms involved. Well, then you can start to see some different effects. So you have to look at, if there's multiple effects going on, you have to look at them individually, just like you would with any system. If you're changing multiple variables at a time, you don't always get a smooth relationship or a smooth trend. Now, of course, why this is possible, right, is when you start putting in bonds, right, you start to add different forms of movement, right? So, you know, everything that's in the gas form, for example, can have translational motion. It can move. But when you start putting bonds in there, then you start getting rotational, right? A single atom isn't going to have rotational motion, right? It's just a single sphere. But if you start having a bond, this atom can rotate in different ways. It can stretch, right? This gives vibrational motion once you have bonds. So you start to give more modes of movement, more ways to disperse the energy, a higher entropy. Now, the last sort of thing that I want to look at here is making a solution. So the one thing that we can always keep in mind is that the dissolved form or the solution form will always have higher entropy than the solid form will, right? So solids will tend to have very low entropy anyway, but creating a solution will always increase the entropy because you're dispersing the energy that was contained within this crystal and you're dispersing it into the entire solution. So you're dispersing that energy. You're always going to increase the entropy when you create a solution. So now we see how various factors of the structure or form of the material can affect its standard entropy. So to close out this section, we want to look at actually how we can calculate, right, our standard entropy of reaction. So now we have our standard entropies, and what you can see here is very much like we saw with enthalpy, where we could calculate the standard enthalpy of reaction by looking at the enthalpies of formation of the products minus the enthalpies of formation of the reactants. Right? We had this equation, if we remember, right? We had delta H of reaction equals the sum of the products, delta H of formation, minus the sum of the reactants, delta H of formation. We have an analogous equation for entropy values. We can calculate the standard change in entropy for the reaction by looking at the sum of the molar entropies of all the products times their coefficients. So we can't forget to do that times the coefficient thing, right? Because these are molar values. So we need to multiply by how many moles are reacting. Minus the sum of all of the standard molar entropies of the reactants multiplied by their coefficients. And so we end up doing the products minus the reactants will give me the change for the reaction. So very analogous to what we did with enthalpy. We're going to pull the values out of the table, plug them into our reaction, and calculate products minus reactants. All right, so that closes this section. I'm going to do a practice problem to follow this up. Okay, so now let's do an example problem. So we're asked to calculate the standard the standard change in entropy for the reaction, and for the following reaction, that 2 moles of H2S gas plus 3 moles of oxygen gas react to give 2 moles of water vapor, and 2 moles of SO2 gas. So we're going to calculate this based on our standard molar entropies. So remember our equation here, right, is the standard molar entropy of the reaction equals the sum of the molar entropies of the products minus the molar entropies of the reactants, again, times their coefficients, right? So reactants here and products here. So I've listed over here what the values are. So you can find these by going again to that table. Some of them will be listed in that small table in the chapter, but all of them will be listed in the appendix in the back of the book. So you just need to look them up there. And we're just going to go through and systematically calculate this value for the products and the reactants and then subtract them. So just for ease of writing it out, I'm going to calculate these two values individually and then we'll subtract them. So let's do the products first. So our products here are water and SO2. So we're going to look up our values right here, right? So we have 2 moles of water. So we're going to have 2 times our 188.8. Again, all of these have units of joules per mole Kelvin. And we're going to add that to 2 times our value for SO2, our 248.2, again, joules per mole Kelvin. And if I calculate that, so my value for the products is going to equal, give you a second here to do the math. So if we calculate it for the products, we're going to get 874 joules per mole Kelvin. And now we're going to do the same thing for our reactants. Again, our reactants are going to be the H2S and the oxygen. So for our reactants, we're going to have 2 times the value for H2S, or 205.8 joules per mole Kelvin. We're going to add that to 3 times the value for oxygen, or 205.2 joules per mole Kelvin. If we add all that up, we get 1027.2 joules per mole Kelvin. And then we plug those two values into our overall equation to get our value for the reaction. We do our products, our 874.0 minus our reactants, 1027.2. And if we do that, we end up with a negative 153.2 joules per mole Kelvin for our delta S of reaction. So we can see this process has an overall decrease in entropy. And this isn't necessarily surprising. If we look at the reaction itself, right, we're going from having 5 moles of gas to only having 4 moles of gas. And that's one of the ways that we can sort of look at a reaction and say whether the entropy is going up or down, is if the moles of gas decrease right? That's going to indicate a decrease in entropy. If the moles of gas would increase, we'd get an increase in entropy. So it's not surprising that we end up with an overall negative entropy change for this process. So that concludes what I want to talk about for this section. In our next lecture, we'll be talking about, again, free energy changes, and we'll learn look at ways to calculate the free energy of reaction, or the standard free energy of reaction, or the delta G of reaction.